Hi, welcome. I'm Timo, and I'm excited to show you our work on event-based eye tracking. Eye tracking is an important technology for building AR and VR headsets, and in this work we show how to provide low-latency eye pose estimates at 1 kHz refresh rates. This fast sampling is motivated by applications like foveated rendering and because the human eye can move at speeds as fast as 500 degrees per second. At the same time, eye tracking has to satisfy constraints like low power, high dynamic range, and be computationally inexpensive. We aim to solve two key challenges of eye tracking. The first is that traditional cameras are wasteful. Most pixels are not informative for eye tracking, but we waste power and compute processing them anyways. Second, the raw image features for eye tracking, like glints of light off the cornea, are computationally expensive to extract. To address this, we turn to event sensors, which unlike traditional cameras operate asynchronously at low latency and low power. Rather than producing entire images at a fixed frame rate, event sensors produce a sparse stream of events. Events are represented as the coordinates of pixels which have increased or decreased in intensity by a tunable threshold, together with microsecond accurate timestamps. One common method of near-eye tracking is illuminating the eye and recording reflected glints on the cornea. Since the positions of the lights are known, you can regress the 3D position of the eye by finding the 2D locations of the lights in the image. We wish to do this with an event sensor. A key challenge, though, is that there are no events if the eye does not move or the lighting doesn't change. Conversely, if the headset moves or the lighting changes, many unwanted spurious events are generated. Prior work solves this through fusion with conventional frames, eliminating the power benefits of event sensors. Our method does not require camera frames, instead using the light sources actively to stimulate the event sensor and produce a robust signal. We flash our LEDs in a high-frequency binary pattern. Ones and zeros are encoded as 300 and 600 microsecond pulses respectively. Using a rolling window, this gives us a 1 kHz update frequency. By applying bandpass filtering in the 300 and 600 microsecond bands, we can reject spurious events from typically low-frequency headset motion and lighting disturbances. This computationally cheap step allows us to identify each glint in the image uniquely by its binary tag. This way, we can also support arbitrarily many glints. Previous works using active LED markers with event cameras have been restricted to using 5 or less light sources. Using flashing lights to illuminate the scene would typically saturate the event sensor as it observes brightness changes at every pixel, costing power and compute at best, and breaking the system at worst. This motivates our second key idea, differential lighting. We replace each LED with a pair of closely spaced LEDs. When one LED turns on, we turn the other off, so they compensate each other. Specular reflections, like in a mirror, are very sensitive to the displacement of the light source, while diffuse reflections, like on a sheet of paper, are not. The overall effect is to amplify the number of events produced at the specular cornea, while nearly eliminating events from the rest of the diffuse facial region. The reduction in net events and increase in signal-to-noise ratio is dramatic, and since event camera power is determined by event rate, saves a further 9 milliwatt of power. We evaluated our design by building a physical prototype and testing with a rotating model eye. Here we plot the results of changing eye rotational speed for various blink frequencies from 250 to 1500 Hz. We achieved sub-pixel glint detection accuracy with the eye rotating at 500 degrees per second up to 1 kHz tracking, although frequencies beyond that decreased in performance due to sensor limitations. Here you see glint detection results for some of the real eye sequences we captured, in real time in the top row and 10 times slower in the bottom. The color-coded circles represent detected glints coming from each LED. In most frames of these real eye saccades and smooth pursuits, we are getting consistent high frame rate glint detections. In conclusion, we have demonstrated the first kilohertz eye tracker based only on events. Our active lighting scheme, differential lighting, selectively amplifies events off specular surfaces in a scene while reducing events from diffuse surfaces which may have application outside eye tracking. Finally, we give a binary coding scheme to efficiently extract features for eye tracking and have evaluated this design with a physical prototype with both model and real eyes.